Hello, everyone. My name is Yiming, and I'm a third-year PhD student from University of Rochester. I'm working with Professor Yu Hao. It's a great honor being here to present our work, Low Latency Proactive Continuous Vision. This work is a collaboration from our group with researchers from Shanghai Jiao Tong University. Continuous vision is a cornerstone of a diverse range of intelligent applications, such as autonomous driving and augmented reality. However, we think that today's continuous vision applications is bottlenecked by the long end-to-end frame latency. This long frame latency significantly impacts the system agility and user experience. We find that the long frame latency is fundamentally caused by the serialized execution model of today's continuous vision pipeline. The traditional continuous vision pipeline looks like this. For the first step, the camera sensors will capture the light information and transform it into digital representations, which is also known as raw pixels. Later on, image signal processor will use raw pixel as input, performing image signal processing algorithms, and generate RGB frames for vision algorithms. We later on refer to these two stages as front end. Finally, the vision algorithms will be processed. And nowadays, deep learning has shown dominant accuracy on vision algorithms. These DNN-based algorithms usually happen on a DNN accelerator, or it's called NPU, and we refer to this one as backend. As we can see, all the three stages are serialized. Even with pipelining, the end-to-end frame latency is still the accumulation of all three stages. Pipelining, along with other commonly used optimizations such as batching, will only contribute to higher throughput, but may cause even longer frame latency. And this is naturally caused by the serialized execution pipeline. So in this work, we present a proactive execution pipeline on continuous vision applications. We propose to use the idea of speculative execution to break the serialization chain of the three stages. And to solve the key challenges raised in this new proactive pipeline, we gave our solutions to make the proactive pipeline practical. Later in this talk, we refer to our work as PVF. In our system, not all frames will follow the same execution pattern. Some will follow the traditional pipelines. For example, for this frame 1, it will execute all three stages in a serialized way. After the front end of the first frame, we will be using the result of the front end, which is a high-quality RGB frames, to predict a sequence of future frames. And the future frames predicted by predictor will be used for further speculation. Notice that because of the continuity in continuous vision scenarios, this type of predicting future frames have a high confidence of being true. And critically, many frame prediction algorithms could predict multiple future frames in a sequence, which allow us to speculatively process multiple outstanding frames at the same time. And in this setting, the frame 2 and frame 3 has been predicted using frame 1. Thus, the vision algorithms can happen on the predictions of frame 2 and frame 3 before the real images are generated, which is a green and orange vision block here. The speculation allows us to break the sequential dependencies among the three stages and to reduce the latency. To ensure the accuracy of the speculation pipeline, before we commit the vision algorithms, we will have a validation process that validates the predict frames with real frames. If, say, the validation of frame 2 fails, where the prediction of frame 2 may be different from real frame 2, we will throw the vision results generated from predict frame 2 and re-execute the vision algorithms on real frame 2. Thus, even with a misprediction, our pipeline is able to handle it with no accuracy loss. If a frame passes the validation, for example, in this figure, the frame 3, we will commit the results generated from predict frame 3. The gain of our system is obvious. For the frames which are accurately predicted, because of the speculative execution on vision algorithms, their latency is largely reduced compared to the traditional serialized execution pipeline. Ideally, the vision latency can be fully reduced. However, the proactive execution pipeline also brings two challenges to the system design. The first one is our predictor will generate multiple frames in a sequence, and we plan to execute them in parallel. This will lead to hardware resource contention and vision computation stage. In this figure, both vision stage of frame 2 and frame 3 will be happening at the same time. If there is only one IP block, then these two parallel processes will have to be serialized, thus break the purpose of speculation. To address the resource contention in the vision computation stage, we propose to explore the hardware heterogeneity available on today's mobile SoCs. We show a figure of Snapdragon 675 SoC here. Same with many state-of-the-art SoCs. It has multiple IP blocks that can be used to execute vision algorithms. For example, in this SoC, the CPU, GPU, DSP, and AI engine, which is also known as NPU, can be used for executing vision algorithms. The second major challenge is the energy overhead. The first energy overhead comes from additional components such as predicting and tracking module. Second, because we're using different IP blocks to solve resource contention, some of the IP blocks are not as energy efficient as NPU. Thus, we propose two ways of reducing energy consumption. As we all know, vision algorithms are inherently tolerant to image quality. So the first one we use is relaxing checking criteria. Instead of using the most strict form of checking, which is to accept a predict frame only when it's a perfect pixel level match, this will lead to unnecessary high misprediction rate and waste of energy. We propose to set a threshold T while validation the predicting frames. A predict frames is accepted as long as its similarity metric is higher than threshold T. Taking relaxed checking one step further, we could skip the checking for a subset of predicted frames that are likely to be similar to the actual frames. In this way, not only checking energy could be saved, the sensor and ISP that generate the actual frames could also be switched off. So basically, in our execution model, the frames can be in three different categories. In a small time slot, the first couple of frames are precise frames. The following frames are predicted frames, where some of them are checked against real frames, and the rest of them are not. We built our system on top of a conventional SoC, where it has multiple computing IPs connected to DRAM through a bus. There are two parts of PVF, the static part and dynamic part, to satisfy two goals of our systems. The first goal is that we want to ensure that speculation does not bring significant accuracy degradation. The second goal is that we want to achieve improvement of frame latency using this proactive execution pipeline while not exceeding the energy budget. PVF first use representative sample data to obtain initial values of similarity threshold T and approximate degree K. We want users to specify their accuracy loss they can tolerate and what type of similarity metrics they want to use. Based on the information we get from the user, we'll determine the threshold T and skip degree K. We enhance the SoC with a predictor. The predictor will be used to predict a sequence of future frames based on the current and previous frames. We have a runtime system that is responsible for three jobs. First, the runtime system will handle the validation of the process. It will compare the results of ISP and predictor when needed, performing checking algorithm, and give whether it's pass or not pass. Second, the runtime will be responsible for scheduling frames. Proactive execution exposes a complex scheduling problem to the runtime system, where multiple predicted frames are to be executed on heterogeneous SoC with multiple execution targets. Different scheduling can result in different frame latency and energy consumption, since different IP has different compute capability and energy consumption. We formulate the scheduling problem into a constraint optimization problem and solve it using a lightweight greedy algorithm that works well. Please refer to the paper for more detail. At last, the runtime have another role, which is the dynamic accuracy control. We propose to use static offline profiling to guarantee accuracy. However, it is possible that the accuracy knob setting offline is occasionally overly aggressive or conservative at runtime. Thus, we propose a control mechanism to handle accuracy performance trade-off during runtime. We now show how PVF will improve the frame latency of continuous vision applications. To demonstrate PVF, we built an in-house simulator to model the state-of-the-art SoC. We measure the latency of DSP, GPU, and CPU on NVIDIA TX1 platform and build RTL implementations for NPU and predictors. The NPU is a 20 by 20 physiological array, and because we're using a learning-based predictor, the predictor is a 10 by 10 physiological array. We evaluate two applications, which are object detection and tracking. For detection, we use YOLOv2 on KD dataset, and for tracking, we use a state-of-the-art tracking algorithm, ECO on VOT dataset. We use different input resolution. we compare PVF with three baselines. The first one is what we call base, where every frame is executed in the traditional way on the fastest IP. We further optimize the backend to formulate a BO baseline. In this case, all the baselines are improved upon base, but still only executed on NPU. And for the third case, we call FCFS, where we assume all the computing IP we use in PVF is available, but the system still don't have proactive execution pipeline. So the scheduler can only use a first come, first serve scheduling methodology. We show the results in this figure. X-axis representing the energy consumption, Y-axis representing the latency reduction. The blue circle is representing our framework. For example, at a 70 millijoule energy budget, PVF could achieve more than 50% of frame latency reduction. With the increase of energy budget, our scheduler can be more aggressively scheduling frames on fast but energy harvesting IPs. The frame latency reduction thus will be increased. However, the latency reduction will saturate at a certain point. After that, keep increasing energy budget will not bring any more improvement because of limitation of hardware resources. Compared to BO, PVF achieves 67.4 latency reduction at the same energy budget, and the number is 17% for FCFS. Long frame latency has become bottleneck for continuous vision. We propose a new proactive vision execution model that breaks the sequential execution of vision pipeline. Specifically, we propose to allow the pipeline front end to predict future frames, the pipeline back end, which is vision computation, then predictively operates on the future frames to reduce frame latency. We incorporate two techniques to overcome the key challenges that arise in deploying proactive vision in mobile systems. Although with less accuracy loss, we recommend to use PVF in non-mission critical systems in order to reduce the risk brought by speculative execution. We thank the collaborators Yuxian, Jingwen, Lele, and Yuhao. Thank you for listening. I'm happy to take questions.